We've all heard the forecasts. Quantum computers will soon outperform classical ones by 1 billion times. They'll crack encryption algorithms that have kept our data safe for decades. They'll design new drugs, optimize complex systems, and propel AI to superhuman levels. But let's not forget that quantum is not just about computing. It's also about communication. The idea of quantum-secured communication is getting closer to reality. Researchers at Toshiba Europe recently demonstrated quantum-encrypted messaging over 254 km of standard telecom networks, using quantum key distribution, or QKD. Now, that's a big deal. Imagine being able to send messages where the very nature of quantum mechanics prevents anyone from eavesdropping or tampering with the message. No more worrying about hacking, no more encrypted files, no more phishing attacks. It's theoretical. Secure communication is a fundamental pillar of modern society. It enables us to trust in transactions, protect sensitive information, and maintain the smooth functioning of our interconnected world. However, as technology advances, so do the threats to our communications. Enter quantum computing, a game-changer in the world of secure communication. The ability to hack encryption algorithms that safeguard our data has raised concerns about the security of our digital interactions. But what if there was a way to transmit information that was theoretically impossible to hack? That's exactly what quantum key distribution offers. In essence, QKD exploits the unique properties of quantum mechanics to establish a secure link between two communicating parties. By leveraging concepts like superposition and entanglement, QKD allows the exchange of encryption keys that can be instantly verified for any interception or alteration. This revolutionary approach ensures that any attempt to eavesdrop on the communication disrupts the quantum state of the system, alerting the users to the intrusion. To understand how it works, picture two people, Alice and Bob, who want to communicate securely. They use a quantum key distribution protocol. Alice generates a random sequence of bits, zeros and ones, which serve as her key. She then sends these bits one by one through a quantum channel to Bob. Each bit is encoded onto a single photon which possesses intrinsic quantum properties. For instance, the photon's polarization can represent either 0 or 1. Upon receiving the photons, Bob measures their quantum properties to decode the message. Importantly, the very act of measurement alters the quantum state of the photon. Now let's introduce Eve, a potential eavesdropper who wants to intercept Alice and Bob's communication. If Eve attempts to measure the photons to decode the message, she'll inevitably alter the quantum state of those particles. This alteration will be registered by Bob's measurement device, alerting him to the presence of an intruder. Once alerted, Alice and Bob can immediately discard the compromised key and establish a new secure connection. This continuous verification process ensures that the key remains secure throughout the communication. The security of QKD stems from the laws of physics rather than complicated mathematical assumptions, making it theoretically unhackable. This level of security is a game changer, especially for applications where conventional encryption is insufficient. Imagine banking, military operations, or diplomatic communications. With QKD, financial transactions can be made virtually tamper-proof, safeguarding against fraud or data breaches. Military operations can rely on secure communications to maintain operational secrecy, and diplomatic negotiations can proceed with the assurance that sensitive information remains confidential. In the era of quantum computing, QKD offers a beacon of security in an evolving threat landscape. While quantum computers pose a threat to conventional encryption, they don't compromise the security of QKD. Quite the opposite. Quantum computers can actually accelerate the process of generating and verifying quantum keys, potentially making secure communication even faster and more efficient. Additionally, the same quantum properties that make QKD secure also enable another exciting prospect, quantum teleportation. While not a direct substitute for secure communication, quantum teleportation can play a significant role in distributing quantum keys. By teleporting quantum states from one location to another, we can extend the reach of QKD networks, connecting geographically dispersed parties. This advancement holds particular promise for global secure communication where physical infrastructure constraints may hinder the establishment of direct quantum links. As research progresses, we can expect to see more practical applications of quantum teleportation in enhancing secure communication. Now, while secure communication is just one area where quantum is making waves, quantum networking is also taking huge steps forward. Scientists at Oxford University have recently developed a new method of distributing quantum information between interconnected, photonically linked modules. Now, this might sound super technical, but it's a really big deal because it's one of the key breakthroughs needed to create the quantum internet. Think of it like this. The quantum internet isn't just about sending messages faster or in larger volumes. It's about sending information in a way that's perfectly secure and absolutely error-free. And it's doing that by using something called quantum entanglement. This is the spooky action at a distance that Einstein was talking about, where two particles are linked together in such a way that what happens to one particle instantaneously affects the other, no matter how far apart they are. This means that if you send one of these entangled particles to a friend halfway around the world, you can be absolutely sure that your message is secure and that nobody tampered with it on the way. But it's not just about security. It's also about efficiency. Quantum computers work by harnessing the power of superposition, where a quantum bit or qubit can be in two states at once. This means that they can perform calculations much faster than traditional computers. And the quantum internet would allow us to share these quantum states instantly across the globe. Imagine being able to collaborate on a quantum computer with someone halfway around the world in real time, working together to solve problems that would take years for a traditional computer to crack. This is the kind of stuff that sci-fi movies are made of. The potential is truly mind-boggling. But here's the best part. It's happening right now. Scientists at Oxford University have successfully demonstrated the distribution of quantum information between interconnected photonic-linked modules. It's a crucial step towards building a scalable quantum network. Their method involves using single photons to encode quantum information, which are then distributed to multiple nodes in the network. At each node, the photons undergo transformations, including changes in frequency and polarization to maintain the integrity of the quantum information. By employing advanced techniques like error correction, the network ensures the reliable transfer of quantum states across different nodes. This achievement brings us closer to realizing the dream of the quantum internet, opening the door to secure communication, instantaneous information sharing, and unprecedented computational capabilities. One of the key elements driving these advancements is the increasing availability and affordability of quantum hardware. Companies like PsiQuantum, a leading provider of trapped ion quantum computers, are making significant strides. Their latest system boasts an impressive 32 qubits, marking a substantial leap forward in quantum computing technology. This development allows researchers to tackle more complex problems and explore new frontiers in quantum science. Moreover, the modular design of PsiQuantum's quantum computers enhances scalability, paving the way for larger systems with increased qubit counts. As the hardware becomes more powerful and accessible, we can anticipate even greater breakthroughs in quantum computing and networking. Okay, so let's talk about PICs. You probably haven't heard of them, but trust me, they're a big deal. PICs, or photonic integrated circuits, are basically like computer chips, but for light instead of electricity. They are tiny structures typically made of materials like silicon and germanium that use optical wavelengths to carry data. This is different from traditional electronics which use electrical signals. PICs offer some massive advantages. First off, they're much faster. Optical signals can travel through PICs at the speed of light literally. This makes them much faster than traditional electronic signals which have to contend with signal loss and jitter. Second, PICs are incredibly efficient. Since they don't generate heat like electronics do, they don't need bulky cooling systems which saves on both cost and complexity. This makes them ideal for large-scale quantum computing and communication systems, which require a ton of processing power and bandwidth. Here's a simple example. Let's say you have two computers connected by a cable. If you were to send a stream of data down that cable, it would take time for that data to get from one computer to the other. There'd be delays and errors along the way. Now, if you were to replace that cable with a PIC, the data would zoom from one computer to the other almost instantly. It would be much more efficient and accurate. So you might be thinking, okay, that's great for regular computing, but what does it have to do with quantum? Well, PICs are becoming a key part of quantum computing and communication systems. They're used to generate, manipulate, and detect single photons, which are the quantum of light. This is important because manipulating photons in a controlled way is essential for performing quantum logic operations and for doing secure encryption and decryption. By using PICs to handle these tasks, quantum systems become faster, more efficient, and more secure. And guess what? This technology is already here. Companies like Intel and Toshiba are already developing PIC-based quantum systems. Intel's 1,700-page roadmap for quantum computing mentions PICs several times, highlighting their importance in the technology. These systems are still in the early stages of development, but they show the incredible potential of PICs for the future of quantum. Overall, the future of quantum is looking brighter than ever. But remember, with great power comes great responsibility. As we delve deeper into this uncharted territory, we must proceed with caution. What if we accidentally open doors to dimensions or forces we can't contain? What if we end up creating new forms of intelligence or life that we can't reason with? The potential benefits are immense, but so are the risks. We're treading on a tightrope between progress and peril, and right now the only thing we can do is hold our breath and hope we don't end up stepping on a reality we can't get back from. Do you think it's safe to mess around with wormholes? How about parallel universes? Our curiosity is boundless, isn't it? But sometimes our thirst for knowledge can lead us into dangerous territories. Some physicists, like David Deutsch, have suggested that quantum computing could prove the existence of these parallel realities. Since quantum systems operate on principles that can be interpreted as interacting across multiple dimensions, could it be possible that a quantum computer, with its power and amplification, might not just solve problems, but also create realities or open doors to worlds beyond our own? That's a scary thought, right? In a way, it's lunacy to take these quantum leaps without fully understanding what we're dealing with. Some might say that it's like handing over control of reality itself to an untested system, one that operates on rules that we're just starting to comprehend. You're talking about systems that don't just run algorithms. They create new states of existence and new dimensions. If the quantum algorithms amplify at this level, what happens when the amplification gets out of hand? What happens when we accidentally invite something into our world, or open a door to a parallel universe where the rules are different, where the laws of physics are altered, where the very fabric of existence is in flux? This fear isn't just speculative. It's grounded in the nature of quantum mechanics. These are systems that function in a way that defies classical understanding. And right now, the cutting-edge advancements happening are mind-blowing. We've seen IBM make a huge commitment to quantum by announcing a $150 billion investment over the next 5 years, with a large chunk dedicated to quantum computing and AI advancements. This kind of funding reflects just how serious the race for quantum supremacy is, and IBM is doubling down on U.S.-based manufacturing for quantum chips, a move that positions the U.S. to maintain its edge in this rapidly evolving field. Meanwhile, Microsoft has unveiled the Majorana 1 chip, which represents a leap into topological quantum computing. This chip is designed to utilize topological qubits, which are more stable and can be less prone to errors than traditional qubits. This is a huge deal because one of the major challenges with quantum computing is dealing with quantum decoherence, where quantum states lose their information due to outside interference. Topological qubits are robust against this, which could open the door to scalable quantum systems that could reach 1 million qubits or more. These developments, while promising, do leave us with a question. Are we tampering with forces beyond our comprehension? Let's explore this further. In the quantum realm, particles can exist in multiple states at once, a concept known as superposition. When these particles interact, their properties blend together in ways that are hard to imagine classically. It's like mixing colors. Red and blue paint together don't make purple paint, but rather a new shade of purple. In quantum mechanics, it's similar but more complex. The combination of two quantum states doesn't create a new state, but rather an entangled state where the particles' fates are intertwined. This entanglement can be extended to large numbers of particles, creating complex webs of quantum relationships. As we delve deeper into this, we find phenomena like quantum tunneling. Imagine a ball rolling toward a hill. Classically, if the ball doesn't have enough energy to reach the top, it will simply roll back down. But in the quantum world, there's a non-zero probability that the ball will simply vanish from the bottom of the hill and reappear at the top, having tunneled through the energy barrier. This isn't a glitch in the system, but a fundamental property of quantum mechanics. It's as if the laws of physics themselves have a sense of adventure, always ready to surprise us with the unexpected. And yet, amid this apparent randomness, there's a deep order, a mathematical beauty that's been revealed by pioneers like Richard Feynman. He showed that every quantum process can be viewed as a path integral, a sum over all possible paths that a particle could take from one point to another. This framework unifies seemingly disparate quantum phenomena under a single mathematical umbrella. It's like realizing that different musical notes played in succession can form chords and harmonies, all based on the same set of notes. Now, let's introduce the concept of a quantum computer. Unlike a conventional computer that uses bits, quantum computers leverage qubits. A qubit can be in a state of 0, 1, or both simultaneously. By manipulating these qubits and their entanglement, quantum computers perform operations that would be prohibitively complex for classical computers. They open up the possibility of solving problems that were previously deemed intractable, like breaking certain encryption algorithms or simulating other quantum systems. However, this immense power comes with challenges. Quantum systems are incredibly fragile. Their states can be easily corrupted by external factors leading to errors. Moreover, the very act of observing a quantum system can change its state, a phenomenon known as the observer effect. This is not just a limitation of our instruments, but a fundamental property of quantum mechanics. It's as if the universe itself recoils from being observed, always changing in response to our attempts to measure it. Now let's talk about decoherence. It's a process by which quantum systems lose their coherence or correlation, essentially becoming less quantum and more classical. This can happen due to interactions with the environment, causing the fragile quantum states to break down into a more stable but less useful classical state. Think of it like a glass of water left on a table. Over time, it evaporates, becoming less and less ordered until it reaches room temperature and blends with the surroundings. Similarly, quantum systems decohere, losing their distinctive quantum properties and becoming less distinguishable from classical systems. Decoherence is a key reason why quantum effects are not easily observable at the macroscopic level. The larger a system becomes, the more susceptible it is to environmental interactions that cause decoherence, leading to a loss of quantum behavior. Now, let's discuss amplification. In the context of quantum mechanics, amplification refers to the process of increasing the strength or magnitude of a quantum state or effect. It's like turning up the volume on a sound wave, but for quantum phenomena. Amplification is crucial for several reasons. First, it helps overcome the inherent fragility of quantum states. Decoherence, which can weaken or destroy quantum properties, is less problematic when quantum states are initially amplified. Second, amplification is essential for certain quantum computations. By amplifying the desired quantum states, quantum computers can enhance the accuracy and efficiency of their calculations. Finally, amplification is vital for tasks like quantum communication and cryptography. By amplifying weak signals or key distributions, we can improve the reliability and security of quantum-based information transfer. One way to amplify quantum states is through a process called quantum cloning. This involves creating multiple copies of an unknown quantum state, effectively amplifying its presence. However, quantum cloning has limitations due to the no-cloning theorem, which states that it's impossible to perfectly clone an arbitrary unknown quantum state. There are workarounds like using entanglement to create approximate clones, but they come with their own challenges. Another approach to amplification is using quantum repeaters. These devices, placed along quantum communication channels, can amplify and correct errors in quantum signals, extending their range and fidelity. In summary, amplification is a vital tool in harnessing quantum properties, but it's a delicate balancing act. Overcoming decoherence, enhancing computation, and improving communication all depend on it. However, striking the right balance is tricky. Excessive amplification can lead to unintended consequences such as increased noise or instability. Thus, controlling and understanding amplification remains a significant challenge and an active area of research in quantum science. So here we are at the precipice of a new era, where quantum mechanics is no longer a theory confined to textbooks, but a tool that we're wielding in the real world. But with great power comes great responsibility. As we decode the secrets of the quantum realm, we must tread carefully, always aware of the potential pitfalls. Because the universe, with its infinite complexities, never ceases to amaze. And who knows, maybe those parallel realities aren't as distant as we think. Maybe they're woven into the very fabric of our existence. All it takes is a quantum leap of faith and a good quantum algorithm to navigate the uncharted territories of the quantum multiverse. Google's recent feat with their new Willow processor pushes the boundaries of what's possible in quantum computing. And if you think that's just a really cool technical achievement, then we're going to have a chat because what you're witnessing is something far more profound. In 5 minutes, the Willow processor solved a mathematical problem that would take a conventional supercomputer 10 septillion years. If that sounds like science fiction, it's because it kind of is. It's a testament to the incredible potential of quantum technology, but also a stark reminder of how much we don't understand about the universe. And here's the thing, we're not just talking about doing calculations faster or storing more data. We're discussing a paradigm shift in how we understand computation, reality itself. The implications of this are far-reaching and, honestly, a bit terrifying. But if you want to understand the true scope of what's happening, you'll need to buckle up and join me on this wild ride through the quantum realm. So let's talk about this calculation. What was it? Why was it so hard and why does it matter? Well, imagine you have a massive box of Legos, and inside that box are all the possible arrangements of those Legos. The calculation that Google's quantum processor solved is essentially finding the shortest path through this box to a specific arrangement. And trust me, even if you have some fancy sorting machines, it's still going to take a really long time. That's because every time you try to find the solution, you have to check every single possibility. And the number of possibilities is staggering. It's a problem called the traveling salesman problem, and it's famously difficult for computers to solve. Now, imagine having a quantum computer. Instead of checking each possibility one at a time, it can check all of them at once. Each Lego arrangement becomes a quantum state, and the computer can examine all of these states simultaneously, dramatically reducing the time it takes to find a solution. That's just one example of what quantum computers can do. But it's a pretty big deal because this kind of optimization is used in lots of real-world applications. Logistics, finance, drug discovery, you name it. If you can find the optimal solution faster, you can make better decisions quicker. But that's just scratching the surface of what's possible. Because the real magic of quantum computers is that they can do things that wouldn't even occur to you. They can simulate other quantum systems, which gives us an unparalleled ability to study and understand phenomena that were previously out of reach. It's like having a microscope that lets you see the smallest particles in the universe. But here's the thing, as you delve deeper into the quantum realm, you start to encounter some weirdness. And, I mean, really weird. Like Schrödinger's cat, weird. Entanglement, superposition, quantum tunneling, these are phenomena that defy our everyday experience and challenge the very foundations of classical physics. At first, it might seem confusing or even contradictory, but that's only because we're used to thinking about the world in classical terms. For example, in the quantum world, a particle can be in two places at once. That's superposition. And two entangled particles can influence each other instantaneously no matter how far apart they are. These concepts might sound like science fiction, but they're very real and have been experimentally verified countless times. They're the stuff that quantum mechanics is made of. But here's where things get really interesting. These quantum properties are not just theoretical curiosities. They have real-world applications. Superposition and entanglement can be used to do secure encryption, quantum teleportation, and even to build quantum networks. And by understanding these principles, we can develop new technologies that were previously unimaginable. However, as we harness these powerful tools, we must tread carefully because there is a darker side to the quantum world. You see, while we are pushing the boundaries of what's possible with quantum technology, there are risks. Quantum computers are extremely fragile. They're sensitive to environmental noise that can cause errors and decoherence. And as we attempt to scale up these systems, the complexity of controlling them increases exponentially. It's a constant battle to maintain the delicate balance that makes quantum computing possible. But that's not all. The very power that makes quantum computers so attractive also presents a significant challenge. As quantum systems become larger and more powerful, they become exponentially harder to simulate on classical computers. This means that the gap between what we can compute classically and what we can compute quantumly is widening. Soon, we'll reach a point where classical computers are simply too limited to keep up with quantum advances, and that could have profound implications for our understanding of the universe. When we reach this point, we'll be entering uncharted territory. We won't have any experience to draw on or precedents to guide us. It will be a brave new world where the rules of computation are rewritten. But amidst these challenges, there is hope. Scientists and engineers are working tirelessly to develop new error correction methods, better ways to control quantum systems, and new algorithms that can take advantage of quantum properties. It's a race against time, but the stakes couldn't be higher. The potential benefits of quantum computing are simply too great to ignore. Imagine being able to simulate the behavior of complex molecules accurately and efficiently. That could revolutionize drug development and materials science. Or consider the impact of secure quantum encryption, which could safeguard our communications and data from hackers and spies. These are just a few examples of what's possible, but the list goes on. However, there's a hidden danger lurking beneath this progress. Quantum computers are not just a tool. They're a window into the deepest secrets of the universe. And as we peer deeper into this quantum abyss, we risk unleashing forces that we cannot control. It's like opening a Pandora's box where, once unleashed, you can't put the lid back on. As quantum systems become more powerful, we'll be able to simulate more complex phenomena. But in doing so, we may stumble upon something we're not prepared for. We could discover new laws of nature that challenge our current understanding, or find ourselves in a position where we can manipulate reality in ways we never imagined. And with that power comes a great responsibility. Think about it. In the wrong hands, quantum technology could be used to create incredibly harmful things. Rogue nations, terrorist groups, even individuals with malicious intent could exploit the power of quantum mechanics for nefarious purposes. It's a scary thought, but it's one that we can't afford to ignore. And here's the most unsettling part. We may not even realize the danger until it's too late. The hidden threats posed by quantum technology may lie dormant for years, even decades, before they come to the surface. And by then, it could be too late to contain them. It's like a sleeping giant that could wake up and wreak havoc if disturbed. So, how do we balance the incredible potential of quantum computing with these hidden dangers? How do we ensure that this powerful technology is used for good and not for evil? These are questions that we must answer as a society. We need to have open and honest discussions about the risks and benefits of quantum technology and work together to mitigate the potential threats. It's a tough balancing act, but the alternative is unthinkable. Imagine a world where quantum weapons are deployed, where data is stolen and manipulated on a massive scale, and where the very fabric of reality is altered in ways we can't predict or control. It's a dystopian nightmare, but it's a possibility we can't dismiss. So, let's talk about it. Let's have the difficult conversations and make the tough decisions necessary to ensure that quantum technology is used responsibly. We have an opportunity to shape the future of our world, but it's a heavy burden. It requires wisdom, foresight, and a deep sense of responsibility. But one thing is clear: we can't afford to be complacent. The hidden dangers of quantum technology are too great to ignore. We must stay vigilant and prepared, ready to face whatever challenges may arise. If you enjoyed this video and would like to support us in exploring more fascinating topics like this one, please hit that subscribe button. Your support helps us continue to push the boundaries of knowledge and bring you the most incredible stories from the quantum realm. So thanks for watching, and I'll catch you next time.